normal distribution is the foundation of regression theory. The bivariate normal distribution is in which x and y are the random variables. The parameters k and m are a function of the means mu sub x and mu sub y, the standard deviation sigma sub x and sigma sub y, and the correlation coefficient rho. The conditional distribution is obtained by dividing the bivariate normal by the univariate normal to yield. As in the case of the bivariate normal, for the conditional normal, the parameters k prime and m prime are a function of the means, the standard deviations, and the correlation coefficient. The conditional normal distribution has the following mean. This equation expresses the linear dependence between x and y. The slope of the regression line is. The conditional normal distribution has the following variance. The correlation coefficient rho is the fraction of the original variance explained or removed by the regression. For rho equal 1, all the variance is removed. For rho equals 0, all the variance remains. Assume two or more random variables that are related. The variable for which values are given is called a predictor variable. The variable for which values must be estimated is called a criterion variable. The equation relating criterion and predictor variables is the prediction equation. The objective of regression analysis is to evaluate the parameters of the prediction equation. Correlation provides a measure of the goodness of fit of the regression. Therefore, while regression provides the parameters of the prediction equation, correlation describes its quality. This distinction is necessary because the predictor and criterion variables cannot be switched unless the correlation coefficient is equal to 1. In hydrologic modeling, regression analysis is useful in model calibration. Correlation is useful in model formulation and verification. The principle of least squares is used in regression analysis as a means of obtaining the best estimate of the parameters of the prediction equation. The principle is based on the minimization of the sum of the squares of the differences between observed and predicted values. The procedure can be used to regress one criterion variable on one or more predictor variables. In one predictor variable regression, the line to be fitted has the following form. The sum of the squares of the differences between y and y prime are minimized. This leads to the parameters of the regression. Since the slope of the regression line is, the estimate from sample data is. Therefore, the correlation coefficient is. The standard error of estimate is the variance of the conditional distribution. For calculations based on sample data, the standard error of estimate is. The regression equations can be used to fit power functions of the type. This equation is linearized by taking the logarithms. With u equal to log x and v equal to log y, this equation is. Replacing x and y for u and v in the equations for the regression parameters leads to multiple regression is the extension of the least square technique to more than one predictor variable. For the case of two predictor variables, the line to be fitted is. The sum of the squares of the differences between the criterion variable y and its estimate y prime is. The minimization of the sum of the squares leads to equations for alpha, beta 1, and beta 2 as a function of the predictor variables x sub 1 and x sub 2 and criterion variable y. The multiple regression equations can be used to fit power functions of the type. This equation is linearized by taking the logarithms. With u equal log of x1, v log of x2, and w log of y, this equation is. Replacing x1, x2, and y for u, v, and w in the equations for the regression parameters leads to